On February 14, 1943, American armored forces encountered German panzers in combat for the first time during the Battle of Kasserine Pass in Tunisia. The engagement exposed critical vulnerabilities in U.S. tank design. Out of approximately 300 M4 Sherman medium tanks committed to the battle, American forces lost 183 vehicles over the course of the 5-day engagement. According to after-action reports compiled by the U.S. Army Ordnance Department, the majority of these losses resulted not from mechanical failure or track damage, but from catastrophic internal fires. British liaison officers embedded with American units documented the phenomenon in field reports submitted to the War Office in March 1943. Their observations indicated that roughly 65% of Sherman tanks penetrated by German anti-tank rounds experienced complete internal combustion. American technical studies conducted at Aberdeen Proving Ground later that spring placed the figure even higher, between 75 and 82% of penetrated vehicles burned completely. The M4 Sherman, which entered production in February 1942, had been designed as a medium tank optimized for mechanical reliability and ease of manufacture. Its welded or cast hull construction, radial aircraft engine or diesel power plant, and 75mm main gun represented sound engineering choices for rapid mass production. However, the ammunition storage arrangement reflected pre-war doctrines that had not anticipated the intensity of anti-tank warfare on the North African front. Standard production Shermans carried between 71 and 97 rounds of 75mm ammunition, depending on the specific variant. These projectiles and their propellant charges were stored in racks distributed throughout the crew compartment, along the sponson walls, beneath the turret basket and in bins on the hull floor. This dispersed storage pattern was intended to maximize crew efficiency during sustained engagements, allowing the loader to access ammunition quickly from multiple locations. The propellant charges posed the primary fire hazard. Each 75mm round consisted of a brass case containing approximately 1.6 pounds of M1 propellant, a nitrocellulose-based powder. When armor-piercing rounds or fragments from high-explosive shells penetrated the Sherman's armor, they frequently struck these ammunition racks. The resulting shower of hot metal and sparks ignited the propellant charges within milliseconds. Once ignition occurred, temperatures inside the crew compartment exceeded 100 to 800 degrees Fahrenheit within seconds. Crew survival rates reflected this reality. Analysis of casualty reports from Tunisia indicated that tank crews had approximately 7 to 12 seconds to evacuate a burning vehicle before conditions became unsurvivable. Commanders and loaders positioned in the turret with access to overhead hatches had the highest survival rates, approximately 40 to 50% in cases of catastrophic fire. Drivers and assistant drivers seated in the forward hull with limited egress options survived in only 15 to 20% of fire incidents. If you're interested in evidence-based World War II military history presented with documentary rigor, please like and subscribe to this channel. Leave a comment indicating where you're watching from. We'd like to know our audience's geographic distribution. The gasoline fuel system, often cited in popular accounts as the primary cause of Sherman fires, actually contributed to a minority of incidents. Engineering studies conducted in 1943 determined that fuel fires accounted for approximately 20 to 25% of vehicle losses. The fuel tanks on most Sherman variants were located in the sponsons, relatively well protected by armor and separated from the crew compartment by bulkheads. While gasoline fires did occur, particularly when vehicles were hit from the side, ammunition fires represented the predominant threat. German anti-tank doctrine during this period emphasized targeting specific areas on enemy tanks to maximize crew casualties and ensure vehicle destruction. Wehrmacht training manuals and Panzerwaffe tactical guides instructed gunners to aim for the turret ring, hull sides at sponson level, and the area directly below the turret, precisely where Sherman ammunition was stored in early production models. The 88mm Flak 36 gun, deployed in the anti-tank role throughout North Africa, could penetrate the Sherman's frontal armor at ranges exceeding 2,000 yards. The 75mm KWK-40 gun mounted on the Panzer IV AUSF. G and later variants could achieve penetration at ranges of 800 to 1,200 yards, depending on impact angle. Both weapons generated sufficient kinetic energy that penetrating rounds and spall fragments easily ignited exposed ammunition. By March 1943, the U.S. Army Ordnance Department recognized that the Sherman's survivability problem required immediate attention. Reports from Tunisia, supplemented by British combat experience from the Western Desert campaigns of 1941-42, provided extensive documentation of the fire hazard. Senior officers, including Lieutenant General Leslie McNair, commanding Army Ground Forces, and Major General Gladian Barnes, chief of the Ordnance Department's Research and Development Service, began advocating for design modifications. The United States Army Ordnance Department initiated a formal investigation into Sherman ammunition fire hazards in April 1943. A technical committee convened at Aberdeen Proving Ground in Maryland, bringing together military engineers, civilian researchers from the automobile and chemical industries, and liaison officers with recent combat experience from North Africa. Initial proposals focused on relocating ammunition storage to less vulnerable areas of the vehicle. Engineers examined the possibility of moving all ammunition to the hull floor beneath the turret basket, where it would be protected by the tank's belly armor. However, calculations showed that concentrating 70+ rounds in the hull floor would raise the vehicle's center of gravity unacceptably, compromising stability on rough terrain and increasing rollover risk. Alternative concepts included installing armored ammunition bins with additional steel plating. Prototype bins with 3/4-inch face-hardened armor were constructed and tested. While these provided modest improvements against shell fragments, they added approximately 1,400 pounds to the vehicle's weight and still offered no protection against direct hits from German 75mm or 88mm rounds. A breakthrough emerged from an unexpected source during a design review meeting in late August 1943. Dr. Martin Coles, a chemical engineer employed by E.I. Dupont de Nemours and Company, who had been contracted to consult on propellant storage issues, proposed surrounding ammunition with liquid fire suppressant. The concept drew on industrial fire safety practices used in chemical manufacturing facilities, where flammable materials were often stored in double-walled containers with liquid barriers. The initial reaction among Ordnance Department officials ranged from skepticism to outright dismissal. Concerns included the added weight of liquid, potential freezing in cold climates, corrosion of ammunition components, and the complexity of maintaining watertight seals in a combat vehicle subject to constant vibration and impact. Nevertheless, the Ordnance Department authorized construction of experimental ammunition bins incorporating liquid jacketing. Early prototypes tested in September 1943 used plain water as the suppressant medium. Engineers built double-walled steel containers with the ammunition stored in the inner compartment and water filling the space between inner and outer walls. The water jacket measured approximately 1.5 inches in thickness. Test firings at Aberdeen Proving Ground demonstrated the concept's potential. German 75mm armor-piercing rounds were fired at prototype bins loaded with inert ammunition. When projectiles penetrated the outer wall and struck the ammunition, the water absorbed much of the kinetic energy and thermal effects. Propellant bags exposed to hot fragments showed significantly delayed ignition times. In many cases, the fragments cooled below ignition temperature before combustion could begin. However, plain water presented multiple problems. At temperatures below 32 degrees Fahrenheit, the water froze, expanding and potentially cracking the ammunition bins. Frozen bins also provided no fire suppression capability. Additionally, standing water promoted rust on steel components and bacterial growth during warm weather, creating maintenance issues. DuPont's chemical engineering team developed an alternative solution, a mixture designated AMUAMP, derived from ammunition and water. The formula consisted of water combined with ethylene glycol as an anti-freeze agent, sodium chromate as a corrosion inhibitor, and trace amounts of copper sulfate to prevent bacterial and algal growth. The mixture remained liquid at temperatures down to -40 degrees Fahrenheit and maintained its fire suppressant properties across a temperature range from Arctic to tropical conditions. Final bin designs completed by December 1943 incorporated several refinements. Ammunition was sealed in rectangular steel containers with double walls. The space between walls, measuring 1 to 2 inches depending on bin location, was filled with approximately 38 gallons of AMWAMP solution, distributed across multiple bins throughout the vehicle. The inner walls were pierced with small drainage holes that allowed the liquid to flow into the crew compartment if a penetrating round breached the outer wall, helping to suppress fires beyond the immediate impact area. The bins were installed in the hull floor and lower sponsons, below the turret basket. This relocation served a dual purpose. It positioned ammunition in the most heavily armored area of the vehicle, protected by both the belly armor and the overlapping side armor, while simultaneously lowering the tank's center of gravity, which actually improved handling characteristics slightly. Ordnance Department officials designated the modification as wet stowage to distinguish it from the previous dry stowage arrangement. The term became standard in military technical documentation throughout 1944 and 1945. Implementation of wet stowage across American tank production required coordination among multiple manufacturers and represented a significant industrial undertaking. By early 1944, Sherman tank production involved 11 primary contractors and hundreds of subcontractors spread across the United States. The Detroit Arsenal tank plant, operated by Chrysler Corporation, had been producing M4A3 Shermans, the variant with the Ford GAA V8 engine, since June 1942. In January 1944, Chrysler engineers received technical specifications for wet stowage installation. The modifications required retooling welding stations, installing new ammunition bin assembly lines, and training workers in the handling procedures for the AMWAMP solution. Chrysler completed the retooling process in approximately 6 weeks without halting production. The company's experience with rapid model changes in automobile manufacturing translated effectively to tank production. The first M4A3 75 WWII Sherman, the W designation indicating wet stowage, rolled off the Detroit Arsenal line on February 21, 1944. Fisher Tank Arsenal in Grand Blanc, Michigan, operated by General Motors, implemented wet stowage in M4A2 production, the variant powered by twin General Motors diesel engines, beginning in late January 1944. The Pressed Steel Car Company facility in Pittsburgh, Pennsylvania, which produced M4A1 Shermans with cast hulls, completed its conversion to wet stowage production in early March 1944. The modification added approximately 900 pounds to the Sherman's combat weight, bringing most variants to between 33 and 34 tons. This increase had minimal impact on mobility. The Sherman's suspension system, derived from the earlier M3 medium tank design, had been engineered with considerable weight margin. The vertical volute spring suspension, VVSS, used on most Shermans, could accommodate the additional load without component stress. From an industrial efficiency standpoint, wet stowage production actually simplified certain aspects of manufacturing. The consolidated ammunition storage in the hull floor reduced the number of small sponson-mounted racks that had previously required individual welding and installation. Labor hours per vehicle decreased slightly, and quality control inspections were easier to conduct with ammunition storage concentrated in fewer locations. Production rates accelerated through spring 1944. In March, American factories delivered 867 new Sherman tanks, of which approximately 340 incorporated wet stowage. By April, the proportion had increased to roughly 60%. In May 1944, the month preceding the Normandy invasion, American plants produced 1,089 Shermans, with approximately 850 featuring wet stowage. By June, virtually all new production incorporated the modification. The Sherman's production numbers during this period dwarf those of comparable German tanks. In the first 6 months of 1944, American industry delivered approximately 5,800 Sherman tanks. During the same period, German factories produced roughly 870 Panther medium tanks and 380 Tiger heavy tanks, a combined output less than 1/4 of American Sherman production. This industrial capacity differential meant that the United States could afford to implement comprehensive modifications across its entire tank fleet rapidly. Germany, facing chronic shortages of steel, labor, and manufacturing capacity by 1944, struggled to incorporate even critical improvements into existing designs. The Panther tank underwent multiple internal modifications throughout 1944 to address reliability issues, but production numbers remained constrained. American forces landed in Normandy on June 6, 1944, but the first wet-stowage Shermans did not participate in the initial assault. The 2nd Armored Division and 3rd Armored Division, which had received substantial numbers of wet-stowage vehicles during May 1944, remained in England until mid-June as operational reserves. The initial armored vehicles supporting the Omaha and Utah Beach landings consisted primarily of older M4A1 and M4A3 variants with dry stowage, along with specialized tanks including the M4A3 105 assault gun and the DD duplex drive swimming Sherman. These vehicles encountered intense German resistance, particularly at Omaha Beach, where elements of the German 352nd Infantry Division occupied well-prepared defensive positions. Combat losses during the first week of operations validated the concerns about Sherman vulnerability. After-action reports from the U.S. 1st Infantry Division and 29th Infantry Division noted numerous tank fires following anti-tank gun hits. However, the specific ammunition storage configuration of destroyed vehicles was not systematically recorded in these early reports. The U.S. 2nd Armored Division, commanded by Major General Edward Brooks, landed in Normandy on June 9th and 10th, 1944. The division's tank inventory included approximately 120 wet-stowage M4A3 Shermans, representing roughly 40% of its medium tank strength. These vehicles were distributed among the division's 3 tank battalions, the 66th, 67th, and 82nd Armored Regiments. Initial engagements occurred during the push towards St. Lo in mid-June. German defensive positions included extensive use of anti-tank guns, particularly the 75mm PaK-40 and 88mm PaK-43. The bocage terrain of Normandy, characterized by dense hedgerows, sunken roads, and small fields, favored defensive operations and limited armor maneuverability. However, maintenance reports from 2nd Armored Division began showing an unusual pattern by late June. Tanks hit by anti-tank rounds and penetrated were being recovered and returned to service at rates significantly higher than historical norms. The division's ordnance companies reported that approximately 60 to 65% of tanks towed to maintenance areas could be repaired and returned to combat status within 72 hours. This represented a substantial change from earlier campaigns. During the Sicily campaign in July-August 1943, only about 35 to 40% of knocked-out Shermans had been repairable. The difference stemmed primarily from the reduction in catastrophic fires. Tanks hit in the ammunition storage area with wet stowage typically suffered localized damage that could be patched, welding new armor plates over penetration holes, replacing damaged internal components, rather than complete destruction requiring vehicle replacement. German armored formations in Normandy during summer 1944 included several elite units with extensive combat experience. The 2nd SS Panzer Division Das Reich had fought on the Eastern Front before redeployment to France in March 1944. The division's Panzer Regiment operated a mix of Panther AOSF, tanks and Panzer IV AOSF, H models, totaling approximately 85 combat-ready tanks by late June. German tactical doctrine emphasized accurate gunnery and exploiting known vulnerabilities in Allied armor. Panzer crews received extensive training in target identification and weak point targeting. Training documents from this period, recovered in Wehrmacht archives after the war, included detailed silhouette drawings of Sherman tanks with specific aim points marked. These aim points corresponded to ammunition storage locations in early production Shermans. The sponson areas where ready ammunition had been stored, the turret basket area, and the hull sides below the turret ring. German gunners were trained to engage these areas preferentially, as hits in these zones had historically produced the highest kill rates. Operation Cobra, the American breakout from Normandy, commenced on July 25, 1944. The operation began with a massive aerial bombardment using B-17 and B-24 heavy bombers, followed by ground attacks by 3 US infantry divisions and 2 armored divisions. The 2nd Armored Division attacked southward from the Marigny area, encountering German defensive positions held by Panzer Lehr Division and elements of 2nd SS Panzer Division. Tank engagements occurred at close ranges, often 400 to 800 yards, due to the terrain restrictions. German after-action reports from units engaged during Operation Cobra noted achieving numerous hits on American tanks, but expressed confusion about the reduced effectiveness of these hits. A report from the 2nd Company, SS Panzer Regiment II, dated July 28, 1944, and recovered from German military archives, stated, "Multiple direct hits were observed on enemy M4 tanks at ranges of 500–700 meters. Penetration was achieved in most cases based on observed impact effects. However, the expected fire development did not occur in many instances. Enemy tanks continued to operate and in several cases returned fire effectively." German intelligence organizations in summer 1944 faced severe systemic problems that hampered their ability to identify and respond to Allied tactical innovations. The Fremde Heere West, Foreign Armies West, the Wehrmacht intelligence branch responsible for Western Front analysis, operated with chronic understaffing and limited resources by mid-1944. Additionally, the German intelligence system had become increasingly fragmented. The Wehrmacht maintained its own intelligence apparatus, but the SS operated parallel intelligence services, and both competed with the Abwehr, military intelligence service. This organizational fragmentation meant that tactical observations from frontline units often failed to reach analytical organizations that could identify broader patterns. When individual panzer crews reported that American tanks were displaying unexpected survivability, these reports were generally attributed to combat stress, misidentification of hit locations, or shooter error. The concept that American tanks had undergone a fundamental internal modification simply did not register as a possibility in German intelligence assessments. By late summer 1944, virtually all Sherman tanks reaching American armored divisions in Europe incorporated wet stowage. The U.S. Third Army, commanded by Lieutenant General George Patton, which became operational in France on August 1, 1944, received almost exclusively wet stowage vehicles during its rapid advance across France. The Battle of Aricourt, fought September 18–29, 1944, in the Lorraine region of eastern France, provided a clear demonstration of wet stowage effectiveness. The engagement pitted the U.S. 4th Armored Division against the German 5th Panzer Army, including the 113th Panzer Brigade, a newly formed unit equipped with approximately 90 Panther tanks. The 113th Panzer Brigade attacked American positions near Aricourt on September 19, 1944, initiating a series of armored engagements that continued for 10 days. German forces achieved numerous hits on American tanks during these battles. The 4th Armored Division's after-action report, filed in October 1944 and accessible in U.S. National Archives records, documented 151 Sherman tanks hit by German fire during the Aricourt engagements. Of these 151 tanks, 41 were classified as total losses, destroyed beyond repair, or abandoned in areas that could not be secured for recovery. The remaining 110 vehicles were recovered to maintenance areas and repaired. Most of these 110 tanks returned to combat service within 5 to 7 days. The 4th Armored Division's Ordnance Battalion commander, Lieutenant Colonel Charles Norton, submitted a detailed technical report on tank battle damage in October 1944. His report noted that approximately 70% of recovered tanks had suffered penetrating hits to areas that would have resulted in catastrophic ammunition fires in earlier Sherman models. With wet stowage, these same hits produced repairable damage. German intelligence assessments of the Aricourt battle, preserved in Wehrmacht operational records, counted all 151 American tanks as destroyed. This error in damage assessment led to significantly flawed operational planning. German commanders believed they had inflicted crippling losses on the 4th Armored Division and planned subsequent operations based on assumptions that American armored strength had been severely reduced. When American counterattacks materialized at full strength, German forces were unprepared for the intensity of resistance. The German military intelligence establishment's failure to identify wet stowage represents a case study in intelligence breakdown under conditions of systemic stress. By late 1944, German intelligence services operated under severe constraints, including manpower shortages, destruction of communication infrastructure from Allied bombing, and the loss of intelligence assets in occupied territories as Allied forces advanced. German forces captured numerous Sherman tanks during 1944-45 operations. Standard procedure called for captured vehicles to be transported to rear area testing facilities for technical evaluation. The Waffenamt, Army Weapons Office, maintained testing grounds at Kummersdorf and Hillersleben, where captured equipment underwent analysis. Several wet stowage Shermans were captured intact during the Battle of the Bulge in December 1944, January 1945. These vehicles were briefly operated by German units. Wehrmacht and SS forces sometimes used captured American vehicles when fuel availability permitted. However, there is no evidence in surviving German technical documentation that the wet stowage system was ever identified or analyzed. The most likely explanation for this oversight involves the fragmentation of German technical intelligence processes by late 1944. Captured vehicles were often examined by field maintenance units rather than specialized intelligence analysts, field mechanics conducting quick assessments to determine if captured vehicles could be made operational would not necessarily investigate internal ammunition storage configurations in detail. Additionally, by late 1944, German technical intelligence priorities had shifted almost entirely to Allied aircraft and electronic warfare systems. Radar technology, proximity-fused artillery shells, and Allied air tactics consumed most available analytical resources. Tank technology received relatively little attention, particularly given that Germany's own tank production had stagnated and resources were increasingly directed toward wonder weapons projects, including jet aircraft and ballistic missiles. The German Ardennes offensive, initiated on December 16, 1944, created conditions for large-scale tank combat in winter terrain. Three German armies, the 6th SS Panzer Army, 5th Panzer Army, and 7th Army, attacked American positions across an 85-mile front in Belgium and Luxembourg. German armored forces included approximately 1,400 tanks and assault guns, representing one of the largest concentrations of German armor in the Western Theater since Normandy. American forces defending the Ardennes included several infantry divisions and elements of the 7th Armored Division and 9th Armored Division. As the German offensive developed, Supreme Headquarters Allied Expeditionary Force, SHAF, committed additional armored units including the 2nd Armored Division, 3rd Armored Division, and elements of the 4th Armored Division. The 761st Tank Battalion, an African-American unit attached to the 26th Infantry Division, participated in defensive operations near Bastogne during late December. The battalion's after-action reports documented numerous instances of tanks sustaining penetrating hits but remaining operational. The unit's maintenance section reported recovering approximately 75% of knocked-out vehicles during January 1945 operations. Weather conditions during the Ardennes offensive included sub-freezing temperatures, often dropping below 20 degrees Fahrenheit at night. The Amuamp solution's anti-freeze properties proved essential under these conditions. Had the wet stowage system used plain water, the liquid would have frozen solid, eliminating fire suppression capability and potentially damaging ammunition bins through ice expansion. Maintenance reports from multiple American armored divisions operating during the Ardennes campaign noted that wet stowage systems continued functioning effectively in extreme cold. No significant problems with frozen ammunition bins were reported, validating the chemical engineering that had gone into developing the Amuamp mixture. By spring 1945, American armored forces crossing the Rhine River and advancing into Germany operated almost exclusively with wet stowage Sherman tanks. The M4A376W, a late production variant mounting the higher velocity 76mm gun and incorporating wet stowage, had become the standard medium tank in most US armored divisions. The 3rd Armored Division, which crossed the Rhine at Remagen in early March 1945, maintained detailed records of combat vehicle losses during its advance across central Germany. Between March 7 and May 8, 1945, the division's Sherman battalions sustained 186 tanks hit by German anti-tank fire. Of these, 29 were destroyed completely, most by mine strikes or close-range Panzerfaust hits that damaged running gear beyond repair. The remaining 157 vehicles were recovered and returned to service. The division's ordnance officer, Major Robert Crisp, submitted a comprehensive report on tank survivability to U.S. Army Ground Forces headquarters in June 1945. His analysis concluded that wet stowage had reduced catastrophic fire losses by approximately 80 to 85% compared to Sicily and Italy campaign data from 1943. German defensive capabilities deteriorated rapidly during the final months of the war. Anti-tank gun availability declined as manufacturing capacity collapsed and transportation networks were destroyed by Allied air attacks. Many German infantry units faced American armor with limited anti-tank weapons, relying primarily on Panzerfaust short-range anti-tank rockets and improvised explosive devices. However, where German forces did employ anti-tank guns effectively, wet stowage continued to provide substantial protection. Engagements around the Ruhr Pocket in April 1945 included encounters with German 88mm anti-tank guns and Jagdpanzer tank destroyers. American after-action reports from these battles documented numerous instances of Sherman tanks surviving hits that would have resulted in fires and total loss in earlier vehicles. The United States War Department commissioned comprehensive studies of tank combat effectiveness beginning in summer 1945. The Armored Force Board at Fort Knox, Kentucky, conducted statistical analysis of tank losses across all theaters of operation from 1942 through 1945. Research teams examined maintenance records, after-action reports, and casualty data from armored divisions that had served in North Africa, Italy, Western Europe, and the Pacific. The objective was to identify which technical modifications and tactical doctrines had proven most effective in improving tank survivability and combat performance. The wet stowage analysis, completed in March 1946, examined data from approximately 3,200 Sherman tanks that had sustained penetrating hits during combat operations. The study categorized vehicles by ammunition storage type, dry stowage or wet stowage, and by date of engagement, type of enemy weapon that achieved penetration, and ultimate disposition of the vehicle. Key findings included: Sherman tanks with dry stowage that sustained penetrating hits experienced catastrophic ammunition fires in 76 to 82% of cases, depending on location of penetration and type of enemy weapon. Hits to sponson areas produced fires in approximately 82% of cases. Hits to hull floor areas produced fires in approximately 68% of cases. Turret penetrations that struck ammunition ready racks produced fires in approximately 88% of cases. Sherman tanks with wet stowage that sustained penetrating hits experienced catastrophic ammunition fires in 10 to 15% of cases across all hit locations. The reduction applied uniformly regardless of enemy weapon type or penetration location. The 10 to 15% figure represented cases where propellant ignited despite the fire suppressant system, typically due to multiple penetrations overwhelming the system's capacity, or hits that directly breached multiple ammunition bins simultaneously. The mortality reduction translated directly into crew survival rates. Tank crews in vehicles with wet stowage had approximately 5 times greater probability of surviving a penetrating hit compared to crews in dry stowage vehicles. The study estimated that wet stowage prevented approximately 4,800 to 5,200 crew fatalities during 1944 to 45 operations in Europe, based on the total number of penetrations recorded and the statistical reduction in fatal fires. From an operational effectiveness standpoint, wet stowage reduced the permanent loss rate of Sherman tanks by approximately 60 to 65%. Tanks that survived ammunition fires could typically be repaired and returned to service, often within 48 to 96 hours. This meant that American armored divisions maintained significantly higher effective tank strength throughout sustained operations. The maintenance and logistics advantages proved substantial. Each Sherman tank represented approximately 22,000 man-hours of manufacturing labor, 30 tons of steel, and the transportation cost of shipping a 33-ton vehicle from American factories to European or Pacific combat zones. By preventing total loss of vehicles that sustained repairable combat damage, wet stowage effectively multiplied American tank production capacity. The M4 Sherman medium tank served as the primary American medium tank throughout World War II, with production totaling approximately 49,200 vehicles between 1942 and 1945. This production figure exceeded all German tank production combined during the same period and represented the largest production run of any tank in history until surpassed by the Soviet T-54 in the 1950s. The Sherman's design philosophy emphasized mechanical reliability, ease of manufacture, and logistical sustainability over maximum armor protection or firepower. This approach reflected American military-industrial strategy, which recognized that technological superiority alone could not determine outcomes in mechanized warfare. Numerical superiority, supply chain efficiency, and the ability to maintain equipment in field conditions were equally critical. Wet stowage exemplified this design philosophy. Rather than attempting to develop armor thick enough to prevent all penetrations, an approach that would have required heavier vehicles, more powerful engines, and substantially reduced production rates, American engineers developed a system that allowed tanks to survive penetrations and continue fighting. The modification also reflected the flexibility of American industrial processes. Implementation of wet stowage across 11 separate manufacturing facilities in approximately 4 months, without significant production disruptions, demonstrated organizational and engineering capabilities that Germany and Japan could not match by 1944. Comparative analysis with German tank development illuminates these differences. The Panther tank, introduced in 1943, featured superior armor protection and a more powerful 75mm gun compared to the Sherman. However, Panther production never exceeded 400 vehicles per month, and reliability problems plagued the design throughout its service life. Final drive failures, engine fires, and transmission problems meant that substantial numbers of Panthers were lost to mechanical breakdowns rather than enemy action. The Sherman, by contrast, achieved exemplary mechanical reliability. Average operational availability rates, the percentage of vehicles in a unit that were mechanically functional at any given time, exceeded 85% for Sherman-equipped units throughout 1944-45. This reliability, combined with wet stowage survivability improvements, meant that American armored divisions consistently maintained higher effective combat strength than German equivalents. Assessing the strategic impact of wet stowage requires examining its effect on operational-level warfare rather than individual tactical engagements. The modification influenced the broader course of the Western European campaign in several ways. First, improved tank survivability directly translated into sustained offensive tempo. American armored divisions could maintain continuous operations for longer periods because they lost fewer vehicles permanently. During the pursuit across France in August-September 1944, U.S. armored divisions advanced 400 to 600 miles in approximately 6 weeks while engaged in frequent combat. Maintenance data indicates that these divisions would have required significantly longer operational pauses to replace destroyed vehicles if losses had occurred at 1943 rates. Second, wet stowage reduced personnel casualties among tank crews, a critical factor given that training a competent tank crew required 4 to 6 months. The U.S. Armored Force faced chronic shortages of trained replacement crews throughout 1944-45. Each crew preserved through improved survivability meant one less crew that had to be trained and transported from the United States. Third, the modification imposed psychological costs on German forces. When German anti-tank gunners and panzer crews consistently achieved hits without corresponding kills, it eroded confidence in weapons and tactics. Several German after-action reports from late 1944 and early 1945 expressed frustration with the apparent ineffectiveness of anti-tank weapons against American armor. While these reports did not identify wet stowage as the cause, they reflected the cumulative impact of fighting an enemy whose equipment performed better than intelligence assessments predicted. Finally, wet stowage contributed to maintaining Allied material superiority at a time when German resistance had stiffened considerably. During autumn 1944 and winter 1944-45, German forces conducted more effective defensive operations than they had during the summer pursuit. If American armor losses had continued at earlier rates during this period, the material balance might have shifted sufficiently to prolong the war. Quantifying this impact precisely is impossible. Historical events result from multiple simultaneous factors, and isolating the effect of any single variable requires assumptions about counterfactual alternatives. However, comparing actual operational outcomes with projected outcomes based on 1943 loss rates provides a rough estimate of wet stowage's contribution. If American armored divisions had lost vehicles at the same rate during 1944-45 as during the Tunisia and Sicily campaigns, total Sherman losses in Europe would have been approximately 8,000 to 9,000 vehicles higher than actually occurred. Replacing those additional losses would have required either reducing the number of active armored divisions or accepting periods of significantly reduced tank availability in existing divisions. Either option would have slowed Allied offensive operations. British Commonwealth forces, which also operated large numbers of Sherman tanks, did not implement wet stowage as rapidly as American forces. British-operated Shermans received the modification beginning in late 1944, but substantial numbers of dry stowage vehicles remained in service through the end of the war. British tank loss rates reflected this difference. Canadian and British armoured units in northwest Europe sustained proportionally higher losses than equivalent American units during comparable operations in late 1944 and early 1945. The wet stowage modification to the M4 Sherman tank represents a category of military innovation that rarely receives historical attention, incremental improvements to existing equipment that produce cumulative effects exceeding their individual significance. Unlike dramatic technological breakthroughs or revolutionary weapons systems, such modifications lack the narrative appeal that attracts popular interest. Yet these unglamorous improvements often determine operational outcomes more effectively than headline-grabbing innovations. Wet stowage saved thousands of lives, preserved irreplaceable military equipment, and contributed measurably to Allied victory in Western Europe. It accomplished these results through careful engineering, rapid industrial implementation, and the systematic application of combat experience to technical problem-solving. The German failure to identify this modification illustrates the vulnerabilities of intelligence systems under extreme stress. By 1944, Germany's military intelligence apparatus had deteriorated to the point where it could no longer process tactical information effectively. This intelligence blindness extended across multiple domains. German forces remained largely unaware of Allied technological and tactical innovations, including proximity-fused artillery shells, improved tank ammunition, and radio-controlled tank destroyers until these capabilities directly affected battlefield outcomes. The wet stowage story offers lessons for contemporary military organizations. Equipment modifications that improve survivability and maintainability may provide greater operational value than pursuing marginal improvements in offensive capability. Industrial flexibility and the capacity to implement modifications rapidly across large equipment fleets represent strategic advantages potentially more valuable than technological sophistication in individual systems. And intelligence organizations must maintain capacity to identify incremental improvements in adversary equipment, not merely focus on revolutionary developments. For the tank crews who served in Sherman tanks during World War II, wet stowage represented the difference between survival and death in burning steel coffins. Their testimony, preserved in unit histories and veteran interviews, consistently emphasizes the modification's importance. One veteran of the 4th Armored Division, interviewed for the U.S. Army's Oral History program in 1983, stated, We knew the Sherman couldn't match a Panther gun for gun, but we also knew that if we got hit, we had a decent chance of getting out alive. That knowledge changes everything about how you fight. That confidence, multiplied across thousands of tank crews in hundreds of engagements, contributed immeasurably to Allied success. The simple innovation of surrounding ammunition with liquid fire suppressant changed the calculus of armored warfare in ways that German forces never recognized and could not counter.